is a good talk. It's one of my most popular talks, and it's very relevant this time of year. With springtime, there's storms, there's lightning. Now, has anybody had their station or house struck by lightning?
Close.
Close?
I took out a laptop, had a network wire running from upstairs to downstairs outside.
I had a spark come out of the end of the coax that wasn't hooked up to anything.
Yeah, that happens. That happens when it snows sometimes, too.
I've had that happen.
Yeah, you hear a little crackling and...
Where I live, there's a utility pole that brings the power between me and my neighbor. The bolt struck that, zapped both our houses, and it went to ground my well, and it blew out.
As it should.
Yeah, as it should, as it was designed to do.
Yeah.
But,
God designed
it blew
it
out
that way.
a lot of. In fact, I smelled smoke.
Yeah, my cousin had a Mazda in Brooklyn, and the lightning hit the street lamp above him, took out the entire electrical system of the car. Insurance company wouldn't pay, and he had to just scrap it to the mechanic.
Lightning will do interesting things, and it will continue to do interesting
It
things.
blew plaster off the walls.
Yep.
I got into the metal lathing and vaporized the water that was in my house. It exploded off the wall.
I've gotten hit twice in my life. The station-
Personally or your house?
No, the house. The house. Not me. Not me.
Move.
Well, I did. The first time was in Warminster, Pennsylvania, and in my station, I had a pretty sophisticated VHF station with a couple of towers, and I was new to the whole thing. The grounding techniques that I was using didn't necessarily, they weren't up to par. And I remember for the 110 volts to turn the station on and off, I had two 20-volt things, but most everything was 110. So I had one of the old boxes that had two screw-in fuses. Remember those?
Yeah.
And I had a piece of BX cable, and it went to a plug into the wall, and then the rest of it went to the station. Well, the station was off when I got hit, and both fuses were blown. The plug was welded into the socket. It took, I was like trying to get it out. And it blew out all kinds of other stuff, preamps and power supplies and things. Here in Danbury, not in the house I currently live in, but the other house, which is about 1,000 feet as the crow flies, I got a hit, which I think was pretty much a direct hit. One of the clues was I had a bird power meter. Everybody knows what a bird power meter is. Just a meter.
The 43.
Yeah. So I had the element, and it was on the top of the tower on a VHF antenna. And cable came down, and then it was an older one with a really interesting looking head on the needle. It wasn't just a straight, it had like a little heart shape or something. So anyhow, the needle was actually vaporized against the glass, and the glass was shattered. So, and there was no needle left on, it was like a little stub at the bottom. That was, let me see, my dryer motor went. The well actually did. The well was okay. My had sort of a high-end stereo system, and the receiver went away. The preamp had all its internals splattered against the back of the chassis. The FM antenna, which was one of those Radio Shack crossed antennas, I had
I have one of them.
Yeah. No, it's a good antenna.
Went right up in smoke, right?
Well, no, the antenna was okay. The coax coming down was missing the center conductor, and it looked like somebody took an X-Acto knife and just went right up and split it open. And where the copper center conductor was just dark matter. not gray matter, dark matter. So, that one was very expensive. And I had the insurance adjuster come over, and we were going through the list. I mean, I had a list of stuff that was broken. The problem with all this is that, let's say you have a very expensive piece of electronics, you know, like a brand new rig, a 7300 or a nice Flex 6400 or whatever it is. When you get lightning that hits things, the chips, the semiconductor chips, will continue to fail. They may work today, but 6 months later, they may fail. And that's just the nature of what's happening. So I repaired some equipment at one point, and actually it was working fine, and then all of a sudden another chip went out, and then another one went out. And I started looking at the path and the schematic, and they were all like in series. They're buffer amplifiers and things. So anyhow, it's interesting what it can do. So the question is how to prevent the problems from happening, okay? Because when it does, it's expensive. So anyhow, this is a little bit about the field organization, but yeah. Okay, so we're going to talk about the power of lightning. Pretty incredible when a bolt hits something, okay? What is a ground? You know, you said your well went away. Well, that's the best ground. Lightning seeks the lowest impedance, okay? How do you design a lightning protection system? You know, how do you protect your amateur station? I mean, you could have just an end-fed wire out the window with a piece of coax underneath the windowsill. You know, you close the window on it, and boom, you get hit. That could, you know, maybe your rig is next to your TV and your stereo system. Well, it could take everything out just from that wire being outside. Or you could have lightning that hits the ground, and the pulse, EMP, electromagnetic pulse, could couple over into your AC mains on the house. Okay, so there's ways to protect all this stuff. Let's see. Whoop, I'll give it another shot, or is it still next slide? Yeah. Okay, so what is a lightning strike? Well, basically, it's the potential. You know, and it's an arc, and an arc goes between, you know, pluses and minuses. In this little cartoon up there, you've got a cloud, and oh, look at that! Yeah, and the arc goes between the pluses and minuses, and that charge builds up, and that's based on. You could be walking across the floor in the wintertime when it's dry out, and you touch the doorknob, right, and you get a spark. Well, that's the same concept, but this is on a bigger scale. So you have polarization changes, and rising moisture, it creates that charge, and then what happens is it discharges. It's like a big capacitor, boom. And that's basically how that arc starts. Okay, next slide. Yep. So air is a great insulator, but you know, air, depending upon how level of humidity, it could be less of an insulator. Okay, so it can always break down, but if the voltage gets high enough, it'll discharge. So basically, your ionized air will turn into a low impedance plasma discharge. And a plasma, it could be like your fluorescent light. You know, plasma is the fourth state of matter. And it basically provides a low impedance path, and that continues to conduct that lightning from where it starts to where it ends. You look at some of the speeds, 60 miles per second, up to 50,000 miles per second. Take a look at the amp. the strike current, 30,000 to 250,000 amps. And that could be in a very small spot. That's a lot of current. That'll do a lot of heating. Just a little bit of an aside, on all the new cars, you see nice aluminum wheels, and sometimes those wheels have chrome plating on them, you know, nice shiny plating. All of that material is not plated in chemicals, it's done in a vacuum. It's a deposition process, and it's using something called cathodic arc process. So it's like a little lightning storm going around, blasting off the material, which typically is aluminum, shiny aluminum, and it's like a little lightning. And the arc spots, we did some calculations, because that's one of the business areas that I'm involved with. And the arc spots have so much current that it just blasts the molecules of the aluminum or the other kinds of materials off. So that's a commercial use for lightning, but on a smaller scale.
You ready for the loaded question?
Yeah.
Is 250,000 amps enough to fully charge a flux capacitor? Did you ever get that question?
It very much could be.
I keep thinking of that Brooklyn. Can't get it out of my head.
Got to launch it.
Yeah, really. Here we go.
Okay, well, everybody has a station like on the top there, you know.
Oh,
it's-
yeah. Of course. Sure. Holy Jesus. Where is
So-
this? Yeah.
I don't know. This is just, I got this off the web somewhere. I don't remember exactly whose, but
CIA or something.
Contest.
they are listening. So lightning really is not attracted to something. I mean, if you say, well, geez, I don't want lightning to come into my yard, not on my property, you know, can you do something so it doesn't come there? Really not, you know, it's random. It's very random. You could have you could say, well, I don't want to put a tall antenna up. I'm just going to put up a cloud burner, a G5RV antenna at 25 feet, okay? I just want to talk to the guys in the next town. So, but you have 80-foot trees around. Well, lightning could hit a tree and then couple over to the antenna. And then you still have problems because that electric pulse comes down your coax line and into your radio. So, you know, it's random. That's the point of this slide. Okay, so why do you have the damage? Back to lightning seeks the lowest impedance to ground. All that current has to go somewhere. So it runs into the house, it goes into the electric system, it goes into the plumbing system, and down into the well, or into the sewer, or, you know, I have a well and a septic here in the city, maybe you don't. So there you go. Basically, what you have to do in a good grounding system is have a place, a low impedance to shunt or carry that current to ground. Okay, now here's a couple of other interesting things. Let's say you have your house with your shack, it's right here. And then over there is your tower, okay? So you have an antenna, and then the tower usually is supposed to be grounded, and the house is supposed to be grounded, but somehow you don't have these two grounds bonded together. So they're grounds, but they're different. Okay, where does all the damage come from? Damage comes from differences in the ground. You could have two grounded surfaces that when you flow 250,000 amps for some milliseconds through them, they will assume different voltages. And that's where you get problems. So you really have to look at the ground system and how you design it.
So your antenna ground system is usually different than your house ground system.
No, they have to be bonded together. That's key. We'll talk a little bit about different types of grounds. I mean, this is a typical ground rod. It's just something I cut off, but it's steel, it's copper coated. This is tarnished because it's been out there. Oh, it's mushroomed because I beat it into the ground. But this is the size of a ground rod. Typically, these things are 10 feet long, 8 to 10 feet long. On my system, I probably have 15 of them around, and they're bonded together, just so, you know, and I do this, that if something ever happened, and I've been lucky, you know, the system's been up for 8 years, and we've had lots of lightning come over. I've walked out, and I've heard bad things, you know, you have that ominous, that quiet, and all of a sudden you hear zzz, and you go, uh-oh, and then all of a sudden, bang! So we're okay at the moment. So this slide here, what is this? On the left side, going vertical, you have resistance. On the right side, you have rod length. So over here, for those who can't really see, this is 20 amps, or 20 ohms, 40 ohms, 60 ohms, and you can look on how long the rod length is, and then you get your impedance. So the longer the rod that's in the ground, the lower the impedance. Or you can do it through multiple ground rods.
What are the number? I can't see those numbers.
Well, they're
Where's
Two-
good? What's
You're going up
good?
in increments of 2 here on the lower
Yeah.
axis, and increments of 20 up here on the
Yeah.
left axis. For every
Two.
2.2. So for instance, you're just starting off with a reading of
10.
120 ohms and
Ten.
length of,
So you're saying you can drive a rod in 10, 12 feet down?
well,
Yeah, in
Not
Connecticut.
not necessarily in Connecticut.
listen to the segue question, which is, you ready? This being Connecticut,
Yeah, how far can you
how much do you
go?
recommend? Because
How
I've
much
heard a
you
lot
hit
of
a rock?
people, I've heard a lot of people swear by the 3 system, if you will. So 3 at 5 to 6 feet,
Yeah,
which
well,
is kind of reasonable for New England.
you get them in as far as you can get them in, okay? Personally, I have, I have one of those fence post pounders.
Gotcha.
Right.
Okay.
Looks like a piece of steel tube, yeah, with
You
2
drop
handles
away.
on it. A number of years ago, I had a commercial job. I had one of my industrial customers wanted me to put in a dozen ground rods through 6 inches of concrete in his factory because they had a high voltage system. And so I took the job, but I ended up going to Harbor Freight. I bought for $450, and I built it into the cost of the job, an electric jackhammer. And then I fabricated a little piece that fits nicely right over,
Right.
and it's hardened steel, so it fits inside the jackhammer, and the other end fits over here. And you take this 10-foot ground rod, and you get up on a ladder, and you start this. And then you take this big machine, and you stick it up, and if all things go right, it takes about 45 seconds for it to go 10 feet into the ground.
It's amazing how many esoteric tasks I've heard people describe, though, that require a trip to that place.
Yeah.
So I had a guy get a hoist from them the other day to lift down a drill press. Just amazing what Harbor Freight
It
carries.
works. You have to be creative. You have to be creative. Okay, next slide, please. So, longer is better,
There we go.
okay? Bigger is better in this case. So, here's a good effect. 1 rod is 33 ohms, let's say. 2 rods is 15 ohms. 3 rods is 12 ohms. 4 rods is 7 ohms. Okay, so we get an idea of when you parallel these conductors in the ground, the impedance between them, and then you start looking at Ohm's law. Ohm's law always applies. Okay, so you put thousands of amps through some ohms, and you'll get a voltage rise. But if it's less ohms, you're going to get less of a voltage rise or difference between the 2 surfaces.
So these rods are to ground your main electrical system or to ground our ham radio equipment?
Well, it should be one and the same.
They should be tied together, you said.
Remember what I said, if you
Bonded
have different,
together.
if you have different grounds, you're gonna have different voltages. You're gonna have two things that think they're at ground and you get a lightning strike, and all of a sudden the voltages are different, and
Well,
that's what does the damage.
okay, so you'll tell us how we can bond next or soon?
Yeah, yeah.
Okay.
3 ohms is, with a 250,000 amps, 3 ohms is gonna give you a little difficult handling.
Yeah.
250,000 volts.
Well,
Yeah,
let's,
250,000 amps at 3
Let's-
ohms.
let's just say
How do you
that,
deal with that?
well, the problem is if you have a direct hit, all bets are off.
Right.
And most of the time you don't have a direct hit, you have a close hit. Okay, so what you have is conducted electric field, not necessarily direct current coming through.
I would hope.
Through. Well, yeah, oh yeah. Okay, so we have a difference between AC power and RF and lightning grounds. Okay, so the city inspector in Danbury told me this once. I had the plumbing inspector come over to look at a job that I did. I put an above-ground oil tank from a heating system in, and I did a very good job at encasing the copper line going from the oil tank over into the house, and I machined up some plastic PVC electrical boxes, and so he said to me, he goes, he says, you can do it to code, in other words, meet the electrical code, or you could do it right. Because remember, meeting the electrical code is the minimum. Okay, there's always better. It's like the contractor that does the work. Is he just going to meet the spec, or is he going to do a good job for you? So, electrical service entrance grounds typically are a little ground, and they just plunk it in right by the meter, and they run a little wire over into the ground, from the electric box into the ground. And that's the minimum that's going to protect your system. Okay, RF power requires an array, 1, 2, 3. You could take that ground over there, and you could use that one and then put 2 more in. 5 feet away, 3 feet away, whatever you can accommodate. Tie them together with some copper, and you got yourself a good ground, a better ground. You actually should bring your station ground out to that ground and tie it in. Okay. And then you have a good RF ground as well as a good safety ground.
And when that's on the opposite side of the house from the antennas, how many people actually do it?
How do you do it, yeah?
Well, antennas would be, in other words, where did the coaxes come into the
Right.
house? On the opposite side of the house?
Yeah.
Well, then you have to put ground rods on that side of the house. And then perhaps maybe on the inside in the basement, you run a conductor through the rafters, if you have an open set of rafters. If you don't, what I'm trying to say here is you can only do what you can do.
Right.
So you try to make it better, right? If you design it from scratch, if you have nothing, no house, nothing but trees and ground, you design it.
Would you run the ground from one of the electrical boxes to the antenna ground as well?
Well, I would say, if your antenna ground is on, and the antennas are coming in at the other end of the house, I would just do it over there. Because,
So don't tie into the electrical box.
no, I wouldn't tie into the electrical box. Unless you're going to put a ring of ground rods around the house. So, you try to achieve greatness, but you may not get there.
What gauge wire would you use for this, for the grounding to the ground rods?
You should probably use something on the order of number 8 or number 6 wire. Solid is better.
How about aluminum? Use it.
Resistance.
Well,
I mean,
you
people used to use
have
aluminum for the.
typically you have different materials you have copper in the ground rod, and now you have aluminum, and then if you don't use the right chemicals, the NOAA locks or some of the anti-corrosive materials, you're liable to have a problem.
I'm very naive, but I have an electrical box, no antenna, but it's rusty. Is it because it got corroded or something?
Water.
Yeah.
Oh, so it's not a grounding problem like electrical.
You probably have ingress of water somewhere. Yeah.
My rig's on the second floor, I'm in a condo.
Mhm.
How do I don't know how to ground it.
Well, you could put a wire out the window, and
It's like 20 feet up in the air.
well,
Is it?
so there you have you have
Drive
two
a rod-
problems.
I have to drive a rod in the ground after that.
That would be the best.
I don't know if I can do that.
I mean, you have two problems. First problem is a safety problem of protecting the equipment. The second is an RF problem, let's just say, so you don't get interference or you don't, radiate. Your ground system's not supposed to radiate, but 20 feet away, you have an impedance, okay? Especially on 10 meters, let's say. The frequency is high enough that all of a sudden that wire becomes an inductor and could resonate.
Mhm.
So, there are some devices that you can tune that ground, so that'll help.
Like an artificial ground, you mean?
Yeah.
Okay.
Look in the MFJ catalog, you'll see a ground.
I have one. Yeah.
And they do work. They do work.
Yeah.
Okay.
Yeah. You
No,
can build your own,
I
but
actually have one.
so an artificial ground is basically tuning that line, so you're tuning the reactance out of the line at the frequency that you're operating. But then that would be a different adjustment for different frequencies.
That works really well.
Yeah.
Yeah. It's, but again, if you got
That's an
struck by
art-
lightning,
It's gonna blow though.
yeah. And the other interesting thing is that with the rigs today, typically the rigs are 12 volts and you have a power supply. Okay, so if you're grounding the antenna over here and then your electric ground is on the other side of the house at the meter, one could say that it's probably okay, because you are protecting the rig if you put a ground rod on the other side of the house where the antennas come in.
And carry the ARRL insurance.
If you want to play, you got to pay. That's how that works. All right, let's talk about some of the things. I think I probably spent close to $1,000 or more in grounding kinds of things around my shack over the course of time. But you don't have to spend a lot of money if you're clever and you look for some bargains. So again, ground rods, you can go to electrical supply and get ground rods. I mean, they are what they are, and you pay for them, and they're not that expensive. I don't know, what are they, $15, maybe 20. I don't think they're more than $15 for a 10-foot ground rod. You can always borrow hammers or implements to get them into the ground if you can. And I think the reason this was cut off is I couldn't get it all into the ground. That was the piece that was sticking up, and I tripped over it so many times I finally just cut it off. Inside, you can use some braid like this. You know what this is? This is old shield off of RG8 or RG213. So if you have cable that maybe got a little water in it, or it's just old cable, or somebody at the flea market said, here, take this, or buy it for $1, well, you strip it all off, and you can flatten it. I put some lugs on it, and you can use that to connect up your radio to your ground line. You could use a piece of 1/2-inch copper you get at Home Depot, and you drill it, put some brass screws in there. I like 1/4-20s, 1/4-inch diameter screws, and you can do that on the back of your operating table. And then from there, out to your outdoor ground. We have various clamps here. These are various clamps that are used to either hold, to go onto ground wires. Some of these are what you find the cable guys or even the electric utility guys will use. So basically these clamp against the conductor, and then you put your lug under there. This one over here, you have this clamp goes over the conductor, and then the other wire goes in the middle, like here, and you screw it in. So those are 2 types. Here's another kind of ground. This is copper kind of material, and you put it around the pipe. So you can form it like this. You can attach it like this, and then go around like a water pipe or some other pipe in your house. Okay, let's see. Okay, next slide, please. All right, let's talk a little bit about bringing coax into your house. So the coax cable's coming down from the tree or the tower or the roof, and what you have to do is you have to bypass it. Okay, so that's for my coax.
Coax. Using hardline, or what do you got?
Yeah, I got one of everything. So I have some 1 5/8 all the way down to RG58. So, and everything in between. So basically what you want to do is, and there's an assortment. I'm going to pass some of these around. Some of these are the same. Different types of coaxial connectors and lightning arrestors and surge protectors. So the coax comes down from the tree or the roof or the tower, and then typically it goes into the house through a hole that you poked in the side of the siding or through the window. But the right way to do this is that you
Copper.
ground the shield of that coax cable directly to the ground rod. Okay? And this type of lightning arrestor attaches to the coax over here. This is the mounting bracket, it's ground, and it goes to your ground system. And then this goes to the radio. Okay? So this is a big one. This is made by Polyphaser, which makes a lot of amateur and commercial kinds of products. And this has got 7/16 DIN connectors on there. That's the style of connector. Probably not something you'd use in your shack. I use it because I buy a lot of surplus hardline, and I adapt from that down to your standard UHF or Type N connectors. These are more in line of what you would find. This style here does the same thing. This has Type N connectors and a grounded plate. This also has type N connectors, and this is a German version. This is a Schooner, and it has a replaceable plug, so if it gets hit by lightning, you can always replace it, okay? But both of these, the shells have to be grounded to your ground system, and your coax goes through like this. Now, when you go and buy one at a Hamfest like this, somebody's going to try to sell that to you, and you're going to say, well, is it any good? Well, who the hell knows? It's difficult to test, because there's really no good tests, because the tests tend to be destructive. So you could high power it, let's put a high voltage across it and see where it breaks down. That may give you a good idea. But in any event, here are a couple of varieties.
Thicker than my coax.
Here's one, I'll leave it in the wrapper, but this has F connectors on there. So this is for cable TV or coaxial 75 ohm antennas. Here's another version that has BNC connectors on there, and I found these at a flea market, a whole box of brand new ones for $1 a piece. So I said, I'll buy 2 boxes of them, keep them in inventory. But I use them on all kinds of things. I've used these on a 2-meter antenna that's a little one on top of a mini tower that I have. To video lines, I actually have a few cameras around the house, and I put them on my antenna impedance analyzer, my little MFJ device, and I swept it, and it works good up to 450 megahertz. So figure you can put 100 watts through that, but you know, that's a good value. So you can find these around on eBay or wherever. Here's another polyphaser. This is just another form factor. Let's talk about a clever way to actually use a little technology and not spend a whole bunch of money. I want to protect my 2-meter or maybe my 440 antenna that's sitting on the top of the roof or eave or somewhere. And I say, well, I don't want to go spend $50 for that. So you could use, let's go to the next slide. I don't know if this is covered or not. There's a little bit what we were talking about up there about grounding the shields, so we can go past that. Okay, I'm getting ahead of the slides, but this is kind of cool stuff. So I use this technique all the time. What happens, this is for those people that know theory, Fred. What happens when you take a quarter wavelength of line and short one end? And look at the other end.
Frequency where it gets the signal coming back.
Yeah,
So
okay.
it's resonant. See,
So if this is quarter wavelength long, let's say at 2 meters, this is calculated quarter wavelength. And then I take a T connector and I put it up on top like this, and I run this to the antenna, and I run this to the rig. And this end is shorted, and this is quarter wavelength long. What have I got?
I recall, I'm trying to remember which way, it's been a long time.
Take a
Whether it
guess.
appears as a short or an open. So I think in this case it appears as a short.
Well,
No, it's
it'll
open.
appear as an open over here.
Oh, okay, yeah.
Quarter wave, it'll appear as an open.
Yeah.
So if you take this and you put a 50 ohm load over here, and then you put this end into your antenna analyzer, and then you look at this on, since this is, the length is for 2 meters, not this specific length, but I'm just saying this would be for 2 meters. You would see 50 ohms resistive, so that would be 1-to-1 SWR, okay, perfect match. except this is shorted. So what does that do? That gives you a DC short, effectively, at this end, from the center to here. Wow, that's really cool, because that gives you lightning protection. Because you have a shorted antenna.
Clever.
But wait a minute, you could hear. You could do this at any frequency. All you need is to calculate the coax. You could do it at 40 meters. You could do it at 80 meters. You could do it at 160 meters. It just takes really long pieces of cable. But you can't do it at multiple frequencies, which could be a problem at HF. But if it's for VHF, what have I got here? I got a piece of coax, which, somebody will just give to you. I like Teflon coax because you can solder it, it's not going to melt. And you get a coax connector and a T and a little adapter, a couple of cables. And, okay, so you got a few dollars into this. And it's very effective.
Does the coax make a difference, whether it's 213 or 58?
You just run the numbers. What's the velocity factor? What kind of coax is it? What's the spec? You go look it up. And it doesn't matter what it is.
I'm not talking about the size, I'm talking about the effectiveness.
No. Well, if you get a direct hit, it may blow that apart versus
Yeah.
RG8 or 213. But if you get a direct hit, it's all over anyway.
Yeah. Well, certainly that would get rid of the static,
Hang on
right?
for a second. Hang on.
That sounds useful for me.
Okay, so let's go back
Now
to.
wait, you say this is shorted?
Well, no, in
theory.
yes, in theory, it's shorted.
Okay, in theory, all right.
In theory, it's shorted. I just pulled that out of my
Okay.
junk box.
I'm looking at it, I'm trying to figure out.
No, that's just standard.
No.
All right, let's take a look at how everything is set up here. This is called star point grounding.
Quarter wave heat connector.
And typically, you don't want to daisy chain all your radios and electronic devices together. You want to do a star point ground. So this is the center of the star. You have a ground rod, goes to a main distribution point, which could be a big piece of pipe, a big piece of copper strap, and then your computers and your telecom and instrumentation and RF, and this was from commercial thing that I leveraged. But what we're trying to say here is that you could ground the computer and the 12-volt power supplies and some of your radios and other devices, and you go to one main star point and then to ground. So
Now, you're doing power and RF.
in this particular,
But if you only have RF ground by the shack, would you do power there as well?
well, you would probably want to go use your outlet.
Okay.
It's sort of counterproductive, but remember, since your power supply is going from the AC to just DC, and the rig is at DC, you're going to protect the rig.
Okay.
And maybe under some condition of lightning, your power supply may expire prematurely, perhaps. But that costs a whole lot less than the rig.
Yes.
Okay. So here we have the concept, the star point concept in a commercial system where you have a tower, and the cables come down and then they go into a building, and the building has all the equipment. So they have ground rods coming out from the tower. So multiple ground rods, low impedance, less ohms is better. Bigger ground rods are better. More of them are better. Here, there's a whole ring around